Welcome to lesson 10.2, actually 10.3, day 2. Our learning target for this lesson is that you will be able to find the sums of the nth terms of geometric series and sums of infinite geometric series, as well as finishing up our first learning target, which is to be able to find geometric means. Geometric means are a lot like arithmetic means. It's that you have two terms that you know and several terms between them that you don't. And we'll define this in just a second. But for this, it says that there are two means. So just like an arithmetic sequence, we have -4 and then 1, 2 missing terms that we do not know, and then 13.5. So our goal is to figure out what the value is, that recursive formula, oh my God. All right. So finding the indicated series, so we have two terms that are missing. We have to figure out the recursive value. In this case, for a geometric sequence, the value of r, the common ratio, that will get us to the next term and the next term and then to 13.5. So geometric means are actually two or more non-consecutive terms that's actually two non-consecutive terms, the -4 and the 13.5 of a geometric series. And our goal is to actually find the two values between them, the two means between them, or however many means between them. So for this particular one, so those between are called the geometric means. The values between them are called the means of the geometric sequence. So to find this, I'm just going to use my rule, a sub n equals a sub I. In this case, I'm going to pretend this is my first term, a sub 1, times r to the n minus 1 power. Well, I already know this, it's 13.5. And I know my a sub 1 is -4. The value of r is what I don't know, that's what I'm trying to find. My position for this right now is the fourth position, and the other one we're considering the first position, at least in what's available for us to observe of this sequence. So that makes that r cubed, 13.5 equals -4 r cubed. So we just have to solve this equation by taking the 13.5, dividing by -4, and taking the cubed root, or raising it to the 1/3 power. This gives us an r value of -1.5, a common ratio of -1.5. So to continue this recursive pattern, I could, if I want, I now could write the rule for this and do the, use the explicit rule, but I'm just going to keep multiplying it because I just need to find two of them. So I'm going to multiply that by -4, and it's going to give me +6. Then I'm going to multiply it by -1.5, because that's the value of r. I get -9, and I just double check again. And when I multiply by r again, I end up at 13.5. Take a moment to try to find the three means of this geometric sequence. The geometric means of this. There will be three values. They will be decimals, because this one's 0.016. See if you can find the value of r. Stop when you find the value of r. All right. So if you did this correctly, then you should have gotten an r value of 0.2, which is, well, actually, should have gotten an r value of plus or minus 0.2, which is plus or minus 1/5. Why, you may ask? Because when you set up this equation, 0.016 equals 10 times r to the 5 minus 1, and you divided by 10, you had 0.0016 equals r to the 4th. And whenever you take an even root, in solving an equation, you have to do plus or minus. So that is why we have this plus or minus. So there's actually going to be two sets of answers for this particular sequence, because I don't know whether the value of r is positive or negative. So what's going to happen is I'm going to try the positive 1/5 first. I've got 10 times 1/5, which is 2, times 1/5, which is 0.4. Since they did decimals, I'm going to go with decimals. Times 1/5, 0.08. And now I'm going to try it one more time just to make sure that I didn't solve wrong. 0.016, which is what I expected. So that's one possible answer. That's when r is positive 1.5, but I have another possible answer where r is negative 1.5. And so my 3 means these three terms will be very different. Well, actually, not all that much different, just the opposite. And so let's take a look. If I do this times negative 1/5, whoops, I hit the minus sign. I get negative 2. Those two are opposite. Times negative 1/5. Hey, I end up right back at 0.4. Times negative 1/5. I get, by the way, that was 0.4. This is negative 0.08, the opposite of this one. And times negative 1/5, I end right back up at 0.016. So there's actually two possibilities for this particular one. Anytime that you have an even root that you take in solving the equation, you will have that possibility. A geometric series is the sum, obviously series is the sum of the sequence. Sum of a geometric sequence, just like the arithmetic series was the sum of the arithmetic sequence. This one's the geometric sequence. Now, there are a couple ways that I can calculate this. We actually need to look for finite. We're going to do finite formulas. There are two finite formulas, and by finite I mean I actually give you a lower bound and an upper bound, like 16, start at position 16 and go to position 31. Versus infinite, which, well, that is the infinite series. So let's do finite up here. Finite series up here. We're going to have the following formulas for a finite series. So I'm going to do S sub n for this finite series. So I'll actually have an nth term to it. You can either do a sub 1 times 1 minus r to the n over 1 minus r, or S sub n equals a sub 1 minus a sub n times r over 1 minus r. This one you would need the final position. This one you need the final position. This one you need the final term, not the final position. So both formulas can come in handy depending on what you've been given as you attempt a problem. Now, the infinite series. So it's not really noted this way, but I'm going to put S sub infinity. And I'm only doing that to point out the difference between this, I'll put that in parentheses. It really is just the sum. You don't have an infinity there. Where this is S sub n, which tells us we have a final position. That final position or that final term helps us calculate that finite sum. Here, infinitely, there's going to be two possibilities. Take a moment to think about what those possibilities may be. We're going to look at this. I have a series like this. 2, 4, 8, 16, 32, 64. You know this series, right? It's the first one you ever studied when you studied exponential functions. You looked at doubling. Well, this is a geometric sequence with r equals 2. What's going to keep happening to these numbers? They're going to keep increasing in value. Increasing exponentially, not just increasing like a linear function, but actually increasing exponentially. This has a base of 2 and some exponent, okay, which probably is n minus 1 if we put the initial amount in front of it. So this function with this base, you can think about the graph, it's just going to rise infinitely. You think about the domain and the range on this as x approaches infinity, the limit as x approaches infinity is infinity. It's just going to keep growing. This thing's going to keep rising infinitely. And so then take upon that you're adding the numbers together, well, it's just going to keep growing and growing and growing, and your number's going to get very, very large. Not just the output itself, but the sum is going to keep getting extremely large. So if our R value, notice here it's 2, if it's greater than 1, if R is greater than 1, then the sum of the infinite series will be, then there won't be a sum. What you'll have is, you'll actually have what I just talked about the limit. The limit as n approaches infinity on r to the nth power, or whatever our explicit rule is going to be infinity. There is no limit. It's just going to keep growing exponentially larger in terms of the individual values, and you're adding those together. You can't get to a specific value. Now, think about a series like one that we did the other day. Let me just make sure it's not on here. It's not on here. Great. I have 1, and then I have 1/10, then I have 1/100th, and then 1/1000th. My R value is 1/10. These numbers just keep getting smaller and smaller and smaller. And when I add them together, by the way, this one's 0.1 and 0.01 and 0.001, and this pattern continues. So when I take this sequence and turn it into a series, where I'm actually adding the terms together, well, this just gets infinitely smaller. And if you think about this as an exponential function with a fractional, going back again to your understanding from the first semester and from Algebra 2 of a exponential function with a value of r that's less. I think I might have just drawn the wrong graph for that. Give me 1 second. 1 over x. I need to actually change this to 1 over x to the power of, 1 over 10 to the power of x. No, I drew the right graph. It's going to approach 0. And we know this because we've explored these functions, we've seen them. This is a depreciating function, okay? So we have, this is just going to keep getting smaller and smaller, closer and closer to 0. We can see that even with the sequence. You would have said, oh, that sequence itself is going to converge at 0. Well, when I add all those numbers together, I'm going to get 1.111, and it's just going to keep building those ones, right? So it's going to be 1.11 repeated, okay, which I believe is 1/9. No, it would be 1 plus 1/9. That would be 1 and 1/9 is the number that would approach. So it actually, if the geometric sequence is divergent, it's gonna, as you do a series for it, it's going to, there's not gonna be a sum. It's just gonna keep getting bigger and bigger and bigger. So the limit will be infinity. They're not gonna get a sum. But if that R value is less, then that means it's going to be a convergent sequence, and it will have an actual sum. And so here's the formula for that. When R is less than 1, that's the key part though. You can't just automatically say, oh, infinite, I'm going to do this. This only works when the common ratio is less than 1. Then you can find it by doing a sub 1 divided by 1 minus R. So there's our formula for infinite. So in this case, there's no sum. it's just going to grow infinitely larger as the numbers also grow infinitely larger that are in the related sequence. So we have two formulas for finite and one formula that works for infinite when the R value is less than 1. So let's take a look at some of these problems, and we'll get down here to some geometric sums. Find the 11th terms of this. Find the sum of the first 11 terms. So they only gave me 3. Now, if it were not a geometric series, I would have to find all 11 terms and then add them all up. And you'll see that on your quiz review, just like in 10.1, there are some series and some sequences that are not geometric or arithmetic, and you're gonna, if you don't have a rule for it, you're gonna have to write out all the values and add them. But for this, we actually have a rule, and I can take my pick for this one. I'm actually going to choose, well, I need to know the 11th term. If I was going to use this, I'd need to know the final term. Here, I don't need the final term. I'm going to use this formula, S sub n equals A sub 1 times 1 minus r to the n over 1 minus r. So I'm going to plug into my calculator. S sub 11 equals A sub 1 is 7, and I have 1 minus, what is my common ratio? I better find it, because otherwise I can't do this. Divided by a negative 24.5, and then I'm going to take the negative 24.5 and divide it by 7. Each time I get a common ratio of negative 3.5. So because it's negative 3.5, I can do negative 3.5, put it in parentheses, don't just change the sign, okay, because the exponent comes first to the 11th. Well, in this case, since the exponent's odd, I am going to end up changing the sign. But had this been an even exponent, then this would have become positive, and I'd still have that minus sign there. So I got to be careful about that. And this is 1 minus negative 3.5. So that one, because there isn't an exponent on it, I could actually just change to a plus. But I'm not going to do that because I'm lazy and my calculator will let me do this. 1 minus negative 3.5, whoops, said that had to be in parentheses, to the power of 11. Again, be careful, because if that's not in parentheses and you have an even exponent, you're going to have a problem. Also, I'm going to do a double parenthesis because I have my numerator and my denominator inside this whole thing. 1 minus, oops, divided by 1 minus negative 3.5. And you can't see that. So here's what I put in. 7 times 1 minus negative 3.5 to the 11th, close the parentheses on that numerator, divided by 1 minus negative 3.5, and then I close the parentheses for the overall bracket. And it gives me this crazy big number of 1,501,000. 1,501,877.337. And yes, I do need to take my decimal place with it. If it were an ongoing decimal, then I might round it off, but this one is not an ongoing decimal. I need to take all the decimal values. For the next problem, they do not tell me the value of n, but they do tell me what the final term is. So as I'm looking back at my formulas, I'm looking at this going, okay, this one I need the nth position. I don't have it. Could I find it? Yes. I could, use my geometric sequence formula, or my explicit rule for the geometric, which is a sub 1 by r to the n minus 1, and I could plug this number in here, and plug in the first one here, and plug in the common ratio, and plug in position 1, and so I could actually solve for n if I wanted to. It's going to involve some logarithms perhaps, but we've done those, and you should be able to do them still, hopefully. But I'm not going to do that. I'm actually just going to use this formula because I know it. So S sub n, I don't know what it's going to be, equals a sub 1 minus a sub n times r over 1 minus r. So I don't even need to know how many positions I'm adding. It's going to know that. It's going to take care of it for me just doing this. So negative 8 minus the product of 131,072 times negative 4. And then once I have that, I have to divide by 1 minus negative 4. Be careful to put your denominator, right? You should probably do all that first in the calculator, hit enter, and then do this. Or put the numerator in its own set of brackets. I'm not going to do that, but you could. You could do it that way. So I have negative 8 minus 131,072 times negative 4. That's a good number on its own. I'm supposed to divide it by 1 minus negative 4, which is really dividing by 5. So I get an answer of 104,856. So that's how we use the finite formulas for problems like this. Here they told me the first 11 terms, the first n terms, but they gave me the final terms, so I could use that second formula. Now I could do that for letters A and B down here also, because they are from 16 to 31. So yeah, I've got to find those positions, but we might have to talk about that in a second. We've got to make sure first that this is geometric. I do see it is because it's exponential. Let's look at these because these are infinite series. So we have infinite series right here because we see the plus dot dot dot. That means that the series keeps going. So I have 2.5 divided by negative 5 and negative 5 divided by 10, which is both negative 1/2. My R value is negative 1/2 for this one. I'm going to find the R value of letter D as well. 1.32 divided by 0.66 is 2. 0.66 divided by 0.33 is also 2. Here my R value is 2. For these two infinite series, which one is going to have a sum? If you guessed letter C, you are correct. Letter C, because, right, remember it keeps getting smaller, it's going to converge. As a sequence it would converge. The series, though, when I add them together, will have a finite sum. We'll have an actual sum, not a finite. We'll have a sum because the R value is less than 1. So for that, I have to do, when the R value is less than 1, I have to do the sum is a sub 1 over 1 minus R. So I'm going to do 10 over 1 minus negative 1/2, which is really 10 over 1.5. Gives me 6.6. Don't put the 7 down. This is 6.6 repeated, which is actually going to be 6 2/3. For the R value of 2, as you remember, the numbers just keep getting larger and larger and larger. And so the limit on that, as n approaches infinity, is infinity. So I'm never going to have the numbers be able to add anything. So I cannot add this one. The sum is going to grow infinitely larger. I'm not actually going to get a specific numerical value for it. Last example, example 7, geometric sum in sigma notation. Same idea here, same exact idea here, except I'm not using a sub 1, at least for these two, because they don't have the first term. They want me to use other terms. So when I do this, I have to be very careful. Okay? In fact, what I'm going to make sure to be aware of, well, let's take a look. Let's first find the 16th and 31st term. The 16th term, if I plug in 16 into this formula, so I'm going to go to y equals, I could actually find all of them from 16 to 31 and add them, but that would be very time consuming and wasteful of my time on the assessment. So now I have x minus 1. So I put in 16 and I'm going to put in 31. Ooh, I'm going to need to highlight that value because it says e to the 8th. Yikes. Well, highlight it. Don't write e to the 8th. There are digits there. So you need to go over and find out what they are or do it on the main screen of your calculator. So a sub 16 is 16,384. And a sub 31, our final term, is 536870912, which is 538,670,912. We know this is a geometric series. How do I know it's a geometric series? Well, Mr. Ritter, they told you to find the geometric sum. Yeah, but how am I going to know that on an assessment or down the road when I see these types of functions again, either in college or in calculus? I'm going to see that this is an exponential function with a base of 2, meaning my common ratio is 2. Okay? And so I'm going to say, oh, that I can actually use one of my shortcut formulas for instead of finding the 16th through the 31st position. And so what I'm going to do here is go back up to our rules. Here's our rules. If it's finite, I need r in the nth position. And I need a sub 1, but I don't want it to be a sub 1. I'm going to let it be a sub I. Because I'm not doing it from the first position. I only want it from the 16th. So I put this in as the sum's going to be 16,384 times 1 minus r to the n. The n is, I need to find out how many it is. It's not 31. Because I'm not doing all 31 terms. I'm doing 31 minus 16. Don't forget to add the 1 back though. So 31 minus 16 is not 15 terms, it's actually 16 terms. So n in this case is 16. Careful there, you can't do 31. N is going to be 16 total. It's not a 16 because the initial term was 16, it's a 16 because there are 16 terms from here to here. Over 1 minus 2. So I have 16,384 by 1 minus 2 to the 16th divided by 1 minus 2, which is a negative 1. And there's my answer. It's actually 1 billion. 1 billion, that sum is 1,073,725,440. If only our finances could grow that fast. So we found I actually didn't even need the 31st term. Now, if I wanted to, I could have used the other formula, right? Had the first and the 31st term, and then I wouldn't have had to think about how many there are. This formula might have come in handy. I wouldn't have to think about how many positions there are. But if it's not starting at 1, there's not 31 positions. You have to figure out how many positions there are before you use that formula. And letter B, we've got from 4 to 11. 11 minus 4 is 7 plus 1. I've got an n value of 8. There are 8 positions, or 8 terms in this series. And so I'm just going to follow the rule. I know that the r value is, by the way, the r value is the base of the exponential function. That's why it was 2 here. Here the r value is 0.5. I'm going to use the same rule because I can find the first term by doing the following. I can do 120 times 0.5 to the power of, I want the 4th position, 4 minus 1, gives me 15. So a sub 4, my first term, is 15. So the sum of the first 8 positions, starting with position 4, so that's why I have my 15 here, by 1 minus 0.5 to the power of 8, because there are 8 positions, divided by 1 minus 0.5. 15 by 1 minus 0.5. Don't subtract the 1 and the 0.5. That 0.5 has an exponent. Divided by 1 minus 0.5 is 29.9. 29.88 or 29.9. Either one of those is fine. So that'd be the sum of the first 8 for this. Actually, not the first 8, but for this, it would be 29.88. I could get that same value by writing out all 8 terms and adding them up. That would be my first preference. Letter C and letter D, you can see, are an infinite series. We have to be careful though. All right, so here's the real question. Are they going to have values? The answer is, well, look at the rate. Here, r is 0.65. Here, r is 0.8. Those are less than 1. So yes, it actually will have a sum. Those, if I were to write out all the numbers in the sequence, or since we're adding them, all the numbers in the series, you would see that as a sequence, it would converge. So now what I'm going to do is follow the rule for the infinite series, which is a sub 1 over 1 minus r. So what I'm going to do, and I have to be careful, I can choose to do one of the following. I can either find the first term and the second term and then find the sum and subtract the first term, because I don't really want the first term in this infinite series. Or I could actually find the second term and go from there. So I'm going to find the first term. 3 by 0.65 times 1 minus 1 is going to be 0, so it's just going to be 3. That's the initial amount. So a sub 1 equals 3. So the sum would be 3. If I did the sum from 1 to infinity, would actually be 3 over 1 minus r, 1 minus 0.65. So 3 over 1 minus 0.65 is actually a 8.57142857 Now the problem with the way I did that is, though, I did it from the first term to like going infinitely, but I don't want the first term. I want it to start at the second term. Well, since I know a sub 1 is 3, all I have to do is take away that first term's value. So in my calculator, I hit minus 3, and I get that that sum from the second term on will be 5.57. 1428571. Now, you could also get that same number by, instead of you doing the way I did, actually finding the second term's value and plugging it into the formula, and it would still work out. If you haven't already, try that for letter D. For letter D, we are doing the first term all the way up. Keep going and going and going. We want to see what that sum's eventually going to add to. And so we do the first term, a sub 1, well, that's 120. And if you didn't know that, it's right there because there's our explicit rule. When you go to do the review guide, if you're thinking remotely of using this rule, you better make sure that, first off, it's to infinity because you're using the infinite rule. But also, you want to make sure it's geometric before you try using a geometric sum rule. So anyhow, I know it's geometric because it has a constant ratio, a first term, it's an exponential function. A sub 1 is 120, so this sum is equivalent to 120 divided by 1 minus 0.8, which is 0.2. So 120 divided by 0.2 is actually 600. So those are my answers for those two problems. Our assignment that goes along with 10.3, day 2, for your practice to make sure that you understand it and your practice to have a better chance of retaining it for your assessment and hopefully beyond, especially if you're going into calc. Page 615, 33 to 63 odd, and 65 to 67. Have a great day.